Hello. We are going to focus on the last word of this class, that is variational methods in mechanics and design. We are going to discuss implementation of the algorithms that we have already discussed at length, that is the optimality criteria method. We will see it in action today using the software MATLAB. First, we will go through the algorithm one more time and look at the code, every line that is important for us to look at, and then run the optimizations for a bar as well as a beam. The stiffest bar and stiffest beam for given amount of material. Okay. So, let us look at the optimality criteria method that we are going to use. We will first review the structural optimization of a bar problem, talk about the necessary conditions, and then describe the optimality criteria method in brief, because we have already discussed that, and focus on the implementation, which is our main task today. So, this is the statement of the problem where we are trying to minimize mean compliance. If you recall, MC is mean compliance. It is basically work done by the external force, and if you minimize it, that is equivalent to maximizing the stiffness of the bar. And this is the governing equation for the state variable u. U is our state variable, a of x is our design variable, and that design variable we have a resource constraint, that is a volume constraint where V star is there. So, the data for this problem, which we must write, we know the length of the bar, we know the loading P of x, and we know the Young's modulus of the material, and we know V star. These are the things that we know. Okay. So, from here, from the problem statement that we just described, we write the Lagrangian, which is basically objective function, added to that the governing equation with the corresponding Lagrange multiplier function, and then Lagrange multiplier for the constraint and multiplied by the volume constraint. So, we can see what is our f, the integrand pu plus lambda times all of this plus capital lambda. This is lambda is a function of x, whereas this is corresponding to a functional type constraint or global constraint will be a scalar unknown constant, and then the volume constraint here, and then we take variation with respect to a, that is variation of the Lagrangian with respect to a gives us what we call the design equation. This is our design equation, as we had said in the last lecture, that there is no area of cross section in this equation, yet it is a design equation. It gives us design equation, that is what we will discuss and use it today. And this is our adjoint equation, and lambda is the adjoint variable, and it looks similar to our equilibrium equation, and hence we can solve for lambda. There is this equilibrium equation, and this, the difference is there is u prime here, there is lambda prime. Okay. So, we conclude that lambda equal to u, and then we have the complementarity condition here, complementarity condition here, which is lambda times the inequality constraint. Either lambda is 0 or this expression is 0. In this case, we would conclude that lambda cannot be 0, because if in that case this one, if lambda is not 0, then this one need not be 0. Then if it is strictly less than, then we will have a problem. Okay. If lambda is 0, then we will have a problem. If lambda is not equal to 0, it is fine, then this has to be 0, the constraint becomes active. Okay. So, solving the equations, we first see that these two, let me change the color of my ink, from these two we get that lambda equal to u, and then from this one and this one by substituting for lambda prime equal to u prime we get this, and we get the condition which we call optimality criterion E u prime square by lambda equal to 1. And this is what we use in the so called optimality criteria method. What we do is, this is supposed to be 1. So, we multiply our a of x in the kth iteration. Here k refers to kth iteration, kth iteration. Okay. So, what we do is we take an initial guess. Best initial guess is to take a of x to be a uniform function, so that it satisfies the volume constraint. You just take V star divided by L as the area of cross section. So, you satisfy the volume constraint, area is the same for all values of x. Then you multiply this one, what you compute at kth iteration. You have to solve the equilibrium equation, that is this equation, then you will get u and u prime, then the u prime goes here. Anyway, you know Young's modulus. We will describe how we will compute lambda at the kth iteration. Multiply by the a, you will get a plus x for the k plus first iteration, and then keep on repeating it until it converges. What do we mean by convergence here? That a k plus 1 should be equal to a k. In other words, this quantity over here should be equal to 1, and that is exactly what our optimality criteria is. So, convergence is this becomes equal to 1, that will be our convergence. Until that we have to iterate. That is how the optimality criteria method works. So, to make it faster we just do that, but then we introduce a beta here, or slower, depends on what value of beta you take. We can tune the speed of convergence, where you get a k plus 1 based on a kth information, you raise it to an exponent. What should become 1? If you raise it to an exponent, it will still be 1. So, we choose appropriate value of beta. We normally choose 2 or 3, and that is up to us when we are running the code. Once we have it, we have to find this lambda at kth iteration. Okay. For that we use the volume constraint, because volume constraint, the complementarity condition, where we say lambda times constraint equal to 0, either lambda is 0 or constraint is 0. If lambda is 0, we have a problem that equilibrium equation will not be satisfied, because u prime, it would mean that u prime is 0, but u prime is 0, then equilibrium equation will not be satisfied, which is E A u prime plus p equal to 0. Okay. So, that cannot possible. So, lambda should be greater than 0. In that case, the constraint should be active, which is what we have. This is a consequence of active constraint, active constraint. Okay. Since its constraint is active, we have a dx integral equal to v star. Hence, we can take this changed a of x, because when you start optimization iterative process, we take a of x, the initial guess, to satisfy the volume constraint. Now, when you update it in this manner, so this particular one we put for a of x and try to find this lambda. That is what we have done. We have put this new one a k plus 1, that is a k plus 1. We integrate over the length 0 to L, that should be equal to v star. That will enable us to solve for this lambda raised to beta, and hence we get this lambda at kth iteration in this manner. Again, once you know EA, which you have assumed to let the optimization start, that will give us u and u prime, and you would have assumed value of beta, you do everything and you get. In the code, the denominator we are going to denote by lambda 1. Okay. It is not Lagrange multiplier or anything, we are just denoting, so that you can take this algorithm and look at the code and understand how the code in MATLAB is implemented. Okay. Now, we also discuss another thing, which is adding upper and lower bounds on area of cross section. Area of cross section cannot be very large, or it cannot be negative or even close to 0. We wanted to keep it at a min or AL, okay, lower bound that we choose, and then upper bound also that we choose, then corresponding multipliers mu L, and this should be mu U will be there, mu L and mu U will be there. So, because of that, our design equation will have 2 extra terms which are indicated here, minus mu L minus mu U, because AL here we have actually this one should be positive and this should be negative because of the way no sorry, I think what we had is right, okay, because A has negative here and A has positive here, minus mu L plus mu U equal to 0. We do not really need to worry about them, we do not need not compute them unless you are interested in calculating the value of lambda analytically, okay, wherever your lambda value you want to know, it is need not compute, it will come as part of the calculation, as you will see, okay. We did not compute them, we will just go with the idea that area of cross section integrated over the entire domain 0 to L. Now we will have 3 portions, we will have the first portion, second portion, the third portion. First portion is the one that where the area of cross section has reached the lower bound, that is where multiplying area by taking it as AL itself. The L by N is the dx, discretization. You see the integration has become discretization because in the computer when implemented we have to discretize. This is the upper bound portion, and then this is the rest of them, which is controlled by the design equation. So, this is controlled by the design equation, okay. Then you can compute like we did when we did not have lower and upper bounds, only thing is in the numerator we will have a few extra terms, okay. We have to sum over a set where the area of cross sections have been pushed to lower limit, that is if it goes below lower limit AL we push it up, if it goes above upper limit we push it down to AU, okay. That is the difference, and rest of it is the same. So, just reverse of it because it is 1 over lambda raised to beta. So, we have to take the bth root of this whole thing. Again in the code this is denoted like this in the code, in the MATLAB code that we are going to see shortly, okay. This is our algorithm. So, if you look at how the algorithm works, we have AK plus 1 being updated from the kth iteration information, okay, and then we keep on looping. This is our outer loop to update AX. When AX and AXK and AXK plus 1 become equal, meaning this what multiplies it becomes equal to unity as we have said, then we have converged, right. But then inner loop is needed, that inner loop to update the lambda. So, we have another index j here to update lambda. Why do we need to update lambda? Because when you update AK plus 1 in this manner, area in some portions can exceed the lower bound or upper bound. Then you have to push up in the case of lower bound being exceeded, or push down in the case of lower upper bound exceeded. So, when you do that, the lambda value has to be updated because lambda was calculated in the iteration of the inner loop when you begin, assuming that nothing has gone above and below the lower bounds. Now, we are pushing it, we have disturbed the area profile. So, you have to recompute the value of lambda, which is what necessitates this inner loop. So, we have an outer loop and inner loop as indicated here. The outer loop is needed to update area of cross section, that needs the finding of the lambda k at the kth iteration. For that we have to run an inner loop, and when do we stop? We stop when no more elements exceed the upper and lower bounds. Whichever exceed, we push them to the either lower or upper bound as the case may be, but we keep on doing it until there is no change, then we stop the inner loop. So, there is an outer loop that goes repeatedly with the index k, there is an inner loop that goes with the index j. So, that is what is going to happen. So, for every outer loop there will be a few inner loop iterations and then exits, goes to outer loop, and outer loop converges when this quantity becomes equal to 1, and then a k plus 1 gets very close to a k based on the tolerance that we specify in the code. So, let us look at the MATLAB code now. So, this is those of all of you should be aware of MATLAB by now, otherwise you can go to MathWorks website and look at tutorial files. Okay. A percentage sign in MATLAB shows a comment line that will not be executed by MATLAB software. So, you can write your name and things like that. So, for example, this code we have modified it for NPTEL massive online open course. So, course is redundant here. Okay. So, there are some housekeeping commands, meaning that we have to do close all figures that are there, clear all variables, clear screen and hold off. All these are basically what I call housekeeping commands. You have to keep your code in its workspace, everything we have to keep it clean. These are housekeeping commands. It is a good idea to add these lines anytime you write MATLAB code. We are specifying length here, and the comments here say what it is, and data for finite element analysis, because that is what we will use here. We are choosing 100 elements along the length of the bar, and number of nodes in that case will be 1 more than the number of elements. Number of elements is n, which is 100, number of nodes will be 1 more, because if I say I have 2 elements, I have to have 1, 2, 3 nodes. This is 1, 2, these are elements. Because it is a bar, it is just a straight bar. So, we will have 1 more than the number of elements for the number of nodes. Okay. That is straightforward enough, and you can change the number and play with the code. Now, after that we define the length vector. Okay. The ones n by 1, that means that it is a n by 1 array or vector. Okay. And that is magnitude is L by n. So, if we have n elements and length of the bar is L, each element will be of length L divided by number of elements. So, L by n, and then we have this vector containing initial area. Here we are just taking constant 6. Ideally we can take volume that we are going to specify V star divided by number of elements, but it does not matter, it just starts from some uniform guess. We can change the number in the code, and we have the Young's modulus, each of them is given as a n by 1 vector. Okay, because that is how our finite element code, which is part of this code, is implemented. And then we have the x coordinates. For this it is a one dimensional problem. So, it is like this, different nodes are there, we have to give the x coordinate x1, x2, x3, of course until x we have n plus 1 nodes. So, that is x n plus 1, and then n y we do not have any of them, they are just zeros, it is a one dimensional problem, so it is zeros. Okay. Going to the next few lines in the code, we have copied the lines over here to explain, then we will go to MATLAB code in MATLAB software and run it, and we are taking the force here. If you look at these commands, there are these comments here. So, whether you want to put uniformly distributed force, the P of x is like P naught, which in this is taken as 20 units, then you would give this. 20 times 1s n plus 1 by 1, because number of nodes are n plus 1. So, we have to do that. So, f vector that we have will be n plus 1 by 1. Okay. And if you want force at the center, you have to know n by 2 1, you will specify some force, or force at the end f n plus 1 times 1. Okay. So, n plus 1 times 1, you have the force specified at the end. At that time you put a percentage sign here and remove this percentage, it becomes midpoint, then you put back percentage, remove this force at the end. Basically you can specify whatever force you want, algorithm is going to work. Okay. And then there is this connectivity to say which nodes make up an element. So, if I have a bar and several nodes here, let us say this is 32, 33, 34, then 32 and 33 make up, let us say, 32nd element. That is what this connectivity does. And then most important thing for us, the boundary conditions. If you see, we have boundary condition for fixed free, then disp ID 1, that is displacement boundary degree of freedom ID, displacement ID, for the first node value is 0, that is fixed, and free, that is we have a bar, this end is fixed, that end is free. So, this is fixed and free. Okay. Similarly, fixed, then you put 1 and n plus 1, both are specified to be 0, and then free fixed, we have n plus 1 and value is 0. What value? Disp value is what value you are specifying for that node. All these are self explanatory, we are going by line here. And then once you have it, we also have to give the tolerance, that is tolerance is given as 10 power minus 3 here, that is up to you, you can increase it, decrease it, that is going to decide when area of cross section AK plus 1, how close it is to AK when it quits. Okay. That is what we have. And then this eta or beta, okay, that is in the code it is written as eta, actually beta in when I explained it, that is we had something that should eventually be equal to 1, we were raised to beta, right, that is this beta. Here it is taken as 0.3, we are slowing it down rather than speeding up, that is something that you have to decide when you run. And then V star is 20 units, units you can put whatever, these are just numbers here, and AL and AU are here, this is AU upper bound and AL which is lower bound. And then history A, basically it stores everything, you can see how the bar, we start with a uniform bar, how the shape changes, we can see the figure file to see how optimization is being carried out, and that is those commands here. And this is the real implementation. The font is little small here, but since you have the code that is also posted along with this, you will be able to see that more clearly or pause the screen and look at it. So, first thing is we are calling FEM bar, that takes the area of cross section, moment, second moment, this actually is not needed here, this is for a, this is actually length of the bar L here, it is not I, length of the bar, and then Young's modulus, x coordinates, y coordinates are not needed, ncon, number of elements, number of nodes, force vector, disp ID, disp val that we described, all this is input to finite element code, that is going to return u displacement and a little bit of other stuff that we do not need right now. For this discussion, it returns reactions and P internal forces and K singular matrix before displacement boundary conditions are applied, and SE the strain energy. We are interested in U, we use that U to compute U prime using finite difference method. So, this one is finite difference method to compute, it is all numerical now, we are computing finite difference using finite difference method. And then we initiate this lambda 1, which was the numerator of our update scheme that we had pointed out in the slides earlier. Let us go there, so we can look at that quickly. So, we said that this in the code is denoted as lambda 1, okay. That is what we are talking about, that is all of this stuff is lambda 1, okay. That is there in the code. So, we are here lambda 1 and that summation that we do, if you remember that had a summation, that is what we do, and then once you have lambda 1 you compute lambda as lambda 1 by v star raised to 1 over eta. As I said, eta in the code is beta in the slides, is just the symbols, okay, are different, and then you update a j equal to a j, that is kth information, and what should be equal to 1, okay. That is how we update, and there is a iterative loop, you see this number of iterations. So, iteration outer loop starts here, outer loop starts here, okay. And then we are checking by setting a false for the flag, and then checking whether it has reached a max or a min. If it is there, we set it to a max or a min. If it exceeds upper bound, we set it to a max. If it exceeds lower bound, we set it to a min, a L and a U. This is a U and this is a L. We do that, then the inner starts now. So, inner loop begins here, okay. The inner loop that we discussed in the slide, you should go through it carefully. Inner loop begins here, that goes where you check whether it is exceeded or not. When it does not exceed, you update using our usual design equation, otherwise you set it to a max and a min, and then check first when you come, if anything has gone, you assign it, and your up count, that is how many elements are there above which have reached a max, and then how many have reached the lower bound a min or a u and a l. You keep count of that and then use that when you are updating for lambda, and that is over here in terms of computing this lambda 1, okay. Now, you have to take that lambda 1 where you are subtracting that, again it corresponds to the formula we had in the slide. So, up count and down count, we count how many elements have exceeded upper bound and hence are pushed down to upper bound, how many have exceeded lower bound and then pushed up to lower bound. So, all this we have to subtract from V star, remaining one of them we have to use to compute our lambda. So, go back and look at the slide. So, let us do that quickly to see what we are talking about. So, we are talking about this. So, how many have exceeded lower bound and upper bound, that is what we are subtracting from V star. If you see the code, we are subtracting this and this, okay. So, once we do that, we go through it and then finish the inner loop. You can see the text here, but this is inner loop ends here, inner loop ends here. So, it began here, it ends here, okay. So, we are basically taking care of computing lambda in the inner loop, and then it is inside the outer loop, and then finally we store everything, check for convergence. Here is where we are checking for convergence to see how first of all we are storing all the history, so we can update plots, so we can see how optimization is actually working, and that is it. Now, what we will do is we will go to MATLAB software and look at the actual running of the code. So, we go here, I will start MATLAB over here, which I have already started, and the code bar optimization is over here, that you will see on the screen in a minute. So, all the code that I showed you in the slides is exactly listed here, okay. So, you can compare with the slides and here, and the data you can change whatever and do it, okay. What we will do is now we will look at the data 10 units, and this is only for rendering we have diameter, otherwise it is not needed, just to show it in the graphics. Number of elements is 100, we can change to whatever we want. Number of nodes, as we already said, is n, number of elements plus 1, and we have 6 for the uniform initial guess. Young's modulus 210, it is actually gigapascal, but does not matter for looking at the shape. When you solve an actual problem, you put the actual numbers with the correct units and so forth, and we went through all of this. Let us just look at what boundary conditions are. Boundary conditions, only the first node is fixed at 0 value, meaning we are looking at a fixed free condition. Okay. And what is the force? The force commands are up here. We are using uniform distributed force. If you want other ones, they are all over here. We can remove the comment and put them. That is, this one is for midpoint load only, and this is for end point load only. Right now we have uniformly distributed load force P of x equal to P naught, that P naught is 20 units here, and then we have fixed free bar. Let us run this and then see what happens. You will see that how the thing changed. It changed too quickly, it is converging already. Okay. When the cursor comes back over this window, that means that we have converged. Let me look at the figure window. Yeah, it is done. So, just so that you will not miss it, I am going to run again, watch it this time, how it goes iteration wise, and when the command prompt comes back, now it has converged. It converges very quickly. Okay. And you see that it has reached the upper bound over here that we have set, okay, and then reach the lower bound we have set. Let us find out what those values are. A min and A max somewhere. So, A max is 6, A min is 1. Okay. Let us look at the figure. So, it is A max is 6. So, I think the way it is done, I think it is the drawing here does not really show that A min A max, because some scaling must have been done over here. Okay. So, but basically has a max and there is an A min. We can check and see why it is showing breadth of the beam is so much, but here the nature of the thing is important. It is linearly profile, the linear profile here reaches a lower limit and upper limit. Okay. If we change the numbers, it should change actually, but here we are taking from here to here, looks like there is a scale factor of some kind in order to show here. It is only rendering, but actually area profile will be calculated. Okay. Now, what we will do is we will well, I mean, let's try this. If A min is actually working, let me put this as 0 and then run to see if it works. Yeah, it did work. So, the tip point went to 0. So, there is scaling, scale factor does not matter in rendering, there is a scale factor. When you made 0, even after scaling it should come to 0, it became a sharp one here. Okay. A min and A max some value. Okay. Now, what we will do is we will put back this again to, let us say 1 or something. Okay. Now, it rerun it and it is going to go like that. It is not allowed to go to 0, right. It is still working, now it is done. So, now we are going to change the displacement boundary conditions. See, it was a fixed free, let us make it fixed fixed. So, what I will do here is to fix also the other end, that is n plus 1, and I need to add the value because I am fixing it, that should also be 0. It should be fixed bar now. Okay, comma or this, either one is fine. Let us try comma. So, this has not changed. One second, I think we have to put the this one to be semicolon here, disp value also is semicolon. Okay. Okay, now you see it has changed. We have to put semicolon here, 1 and n plus 1 node and the 0 0 value. Fixed, this fixed is tapering down and tapering up. So, fixed one is different. We can also do fixed free fixed. So, I will remove this. So, only n plus 1, the first node is free, the last node is fixed. If we do that, it should show a mirror image of that. So, previously it was tapering that way and making this lower bound, it becomes lower bound, it becomes upper bound. Basically the code works whichever way we want. Okay. And now if you were to play with the forces, so we had different forces here. So, if I want to apply force only at the end, okay, let us take that and I will make it 0, right, that array is needed, and then I will press that only n plus 1 at the end. I would like to put 100, everywhere else it is 0. Okay. The profile, if you see, the profile is going to optimal profile, fixed free, uniform loading, this is the one which you can verify, analytical thing we have done in the in an earlier lecture. Now, if I put constant loading, okay, at not n, because that we have fixed that, the first node, okay, let us see what happens. Then it remains constant, it just adjusts to the volume, and that is it, it has converged already because the prompt came in. So, I will run again to see, very quickly it converges and comes over fixed free, okay, when you put this loading here, okay, at one node. So, we can change it, we can add another node if we want. Let us say I add it at the n by 2, the mid one, okay, somewhere in the midpoint. Let us see, then you see it goes to a min here, it is fixed over here and free. When I load is only midway, I do not need material over here, the algorithm realizes that. Many times when you implement an algorithm like this, it will not miss the intuition that you have, and that you have to check various cases like we are doing now. So, we can basically run everything, all right. So, having seen the barcode, I would like to show you the beam code also, which we have discussed optimal criteria for stiffest structure. So, we will run this beam code now. Okay. Again you can go through all these lines which basically mirrors the barcode, but for the case of beam, where there will be FEM beam that will be called, okay, that we can see instead of bar now we will have the beam code being run. So, if you have FEM beam, that also will be given in the website for you to download to run the code yourself. Okay. Let us run it. Whenever you run, MATLAB asks for changing the folder, which we are doing here. So, it is also, you can see how it changes. Looking at it, we can say it is a fixed beam. It is still, some small changes are still happening. Now, it is not straight line anymore like in the bar. In the case of a beam, this is for uniform transverse loading, that is acting perpendicular to the beam here, and now until the command prompt comes here, it is not done. So, it is still changing slightly, you can see some lines here and there slightly flickering, means that it adjusting, fine tuning according to the tolerance that is specified in this program. Now, it has come back, so it is done, we have fixed beam. So, we can go back and change the boundary conditions. So, if you see in the beam code we have 1, 2, 3, 3 times number of nodes minus 2, 3 times number of nodes minus 1, 3 times number of nodes. Basically every node will have 3 degrees of freedom, x displacement, y displacement, and then rotation, the slope. Okay. So, by specifying 1, 2, 3, I am fixing the beam like cantilever at one end, 1, 2, 3, that is it cannot move in the x direction, it cannot move in the y direction, it cannot rotate also. And same thing I am doing in the right hand side, because 3 star n nodes, 3 star n nodes minus 1, 3 star n nodes minus 2, all are fixed. Okay. If you just want to see what happens if I remove this here, when I remove that, it is going to become like a pin joint, because I am allowing to rotate. Then remember the profile here, it is symmetrical because fixed beam. Now, by removing the 3 star n nodes, I made it like a pin joint. So, let me run this, you will see that it changes. The pin joint actually wants no material there. If I make area of min here equal to 0, it actually become a point. Right now, it is going to a min some value that is specified. Okay. It is still running because the command prompt has not come back. When it comes, we will go. There are some small changes that you cannot see. See how quickly the optimization algorithm converges. We are only being overly careful by giving a very small tolerance value, and it takes some while to put, but you do not see any change, but there is a little change happening. So, I want to show you that if I make a min equal to 0, what happens? Let us try that. A min over here it is 1, let us make it 0. Okay. So, make it 0, yeah, it is going to 0. So, it is becoming a sharp tip, and since over here also it is being sharp tip, now it is actually deciding to go apart and come together, go apart, come together. That is what iteration is happening. Okay, transverse loading is there, instead of becoming 2 beams, it is just adjusting, and finally it went, because you cannot have a 0 because it was going like this. So, this may take a while for it to resolve. Number of maximum iterations you have put, it will be basically it wants to make it, wants to come down, we are allowing it to go to 0, it has gone to 0 and it goes there, it looks like a fish. Okay. So, transverse beam, the loading acting on a fish is, we can say optimal, but that is not correct, it will just looks like a fish. It has now come back, right. Maximum iterations is 50. So, instead of putting 0, let us put 0.5 or something like that, then we will see the effect of that already. Okay. Now, it has some area of cross section, it is not going to 0. This is for fixed and pinned beam. Okay. When it comes back, when it is done, we will get the command prompt and the beam code would have been done. Okay. So, this way we can change the boundary conditions, we can change loading and look at the solutions, optimal solutions for the profile. Okay. Very small tiny changes must be happening here, that is why it is sticking. So, there is some flickering here, there. Okay. So, it is just running until now it is done, command prompt has come back. So, what we will do now, going back to the let us make it like a cantilever. I will remove the other degrees of freedom, completely make the other end free, only 1, 2, 3 left node fixed in x, y and the slope. So, if we do that, then we should see that part, it is coming down like a curve. In the case of a bar it was a straight line, but here it is not, and it just goes to a min at the other part. Okay. So, you should learn by learning it several times. By looking at it, you should be able to guess the boundary condition, it is fixed and free. Okay. We can try lots of different boundary conditions, fixed and guided and many others. Okay. Fixed and guided means that we fix it. Okay. Let me bring back. So, Control Z. So, that will make it 1. Okay. So, going to this displacement boundary conditions, where did it go? Yeah, over here. So, fixed guided means that I will fix the last degree of freedom, that is slope degree of freedom, and I will fix the x thing, but y are allow, meaning that I will have this one, the right hand side is able to move up and down, but cannot rotate. This is not allowed, but can move up and down. So, I have a beam, this right hand side cannot rotate, but it can move up and down. Such a condition is what we have specified. It will give you a slightly different one. It almost looks like fixed, but it is allowed to move there. Okay. That is what we had put, right. So, it looks slightly asymmetric now, slightly, and we can change the boundary condition and look at what happens. Okay. X displacement, y displacement, whichever way you want, we can try all of those. Okay. It is still running, there are fine adjustments being done. Okay. So, I would encourage you to try out these codes, because we will be giving a programming assignment also for you, so that you can try these programs and look at your own optimal profiles and run the programs. In the future lecture, we will have a strongest column design, which again can be done using optimality criteria method. Once you follow the algorithm that we have developed by writing down the Lagrange equations and solving the adjoint equation analytically and getting the optimality condition from the design equation and developing the optimality criteria method, implementation is quite easy. In fact, once you have finite element analysis, doing structure optimization is not at all difficult, it is very straightforward. The code may look long, but it is very clear and it is very easy, and this lecture we compared the code with the algorithm, so you can understand the code that is given. Okay. So, we can run lots of them here. So, I can again go back to cantilever. Let us see how it looks when I change the loading to only point loading. So, let us see where the force is. Force is here. So, now it is force applied on all of them like 1. Okay. So, we can make it uniformly distributed or only at one node. Now, it is going 1 to 1 nodes, all of them it is giving, but we can make only the last one has a moment, anything that we can try, because there are so many. So, once everything is 0, let me comment this line, okay, and give force, okay, that is 3 star n nodes, number of nodes, that is the last degree of freedom, that is I am applying only a moment load. Let me put some 45, does not matter what it is. Okay. If we do that loading, let us see if the code works or blows up. So, we have constant movement. When there is constant movement, we got constant area of cross section, that makes sense. If you go back and look at the analytical thing, constant movement, only movement we applied for a cantilever at the end, then the bending moment is the same throughout the beam, and hence optimal criteria method would tell you that area of cross section, because we assumed second moment of area equal to area of cross section some alpha d square by 12, that is just an alpha, beta equal to 1, then what we get is uniform cross section, that is what it is, it converges very quickly. Instead, if I apply vertical load, okay, that degree of freedom will be 1 less than that. Okay. This becomes a transverse load. Let us see what happens. Yeah. Now, this is the tapering thing that we have. So, it in this case has not reached the upper limit, but has reached the lower limit. Okay. It is still running because command prompt has not come back. Now, it has come back. We can rotate and then see how it looks. Now, it is a profile that is straight and goes like this. Okay. So, yeah, that is how it is. All right. So, if you want again the uniform distributed load, you can have that. So, we can move back and remove, uncomment these things, no comment, run it again for cantilever, it will go back to that. There will be slight difference. Now, it is a little bit curved, whereas earlier no was, when you have only a transverse load at the free end of a cantilever, it becomes straight linear, but if you have a distributed load, it gets a little curved, and you can see this now, yeah, a little curved compared to the one that is there. In fact, one may say that Eiffel Tower, if you remember, that has wind load, which if we assume that it is constant, then it will have a shape. So, look at this shape, does it not remind you of the Eiffel Tower? Because there is a min put, if there is no min, it just goes like a spire. I can make a min equal to 0, it will go there. We will just do that at the last one that we tried. A min was somewhere in the code here, yeah, a min, let us make it 0, okay, then it will just go like a point thing. So, you can already see it is happening. Okay. Once you allow 0, it just goes there with the load that is being there. We will wait for the prompt to come up. So, it is still making some small, it is going to A max and then A min, okay, and that is 0. So, it has become a pointed thing like spires. So, many of these structures that are built were also optimal. They probably did not run all these algorithms, but the intuition guides good structural engineers to come up with optimal solutions, but we have algorithms to get that now. So, let me just turn it around and see how like a church spire coming here with a pointy tip, all right. So, you have the code in our hands now, you can run it and understand how it works and enjoy the code.